Alright, today I'm going to talk about long-run production. Let's start with the concept of the production function. I'll abbreviate. The production function is just going to be a mathematical representation of the maximum output attainable from a given input bundle. In general, we can represent a production function like this, where Q, the quantity of the firm's output, is a function of the quantity of the labor input, L, and the quantity of the capital input, K. So a production function in general form is the quantity of the firm's output is a function of its input usage, where L is units of labor and K units of capital. Let me give you a simple looking production function. It's going to be of the format of a Cobb-Douglas. So here the quantity of the firm's output is given by L times K. So for example, let's put a little table together here. If L is 0 and K is 1, we plug these values in the production function and we see that this firm doesn't produce any output. If L is 1 and K is 1, this firm produces 1 unit of output. And we could just do this for various labor capital input combinations. 2 units of labor, 1 unit of capital gets us 2 units of output. You can try different combinations here, 4 and 6, 24 units of output, and so on. So this is the idea of a production function. We throw in some inputs and we see how much output we can get. A couple important concepts with the production function. Not an entirely new concept is this idea of the marginal product of labor. We talked about that with short-run production. The marginal product of labor, I'll abbreviate MP subscript L, is just going to be the change in output from adding an additional unit of labor. So it's just a change in output from adding an additional unit of labor, holding capital fixed. The marginal product of labor is a slope concept. It is a derivative concept. We'll take the partial derivative of the production function with respect to labor. And if this is our production function, the partial derivative of this with respect to labor, holding capital constant, is just going to be K. The next concept is the marginal product of capital. I'll abbreviate MP subscript K. The marginal product of capital, like the marginal product of labor, is going to be a partial derivative concept. And the partial derivative of this production function is just going to be L. Partial derivative of that production function with respect to capital will just be L. In terms of a definition, very similar to the marginal product of labor. This time it's going to be the change in output or the increase in output from adding an additional unit of capital. So here we're asking how much will our output rise if we add 1 more unit of capital, holding labor fixed. Okay, the next concept I want to talk about that's related to the production function is something called the isoquant. An isoquant is going to be a curve showing different input bundles that can be used to produce a given level of output. So once again, an isoquant is going to be a curve showing different input bundles that can be used to produce a given level of output. This idea is very similar to the indifference curve that we studied in the consumer theory chapter. So let's come up with an isoquant using this production function. Let's let Q equal 100. So the idea of an isoquant in this case would be, let's find various combinations of labor and capital that can produce 100 units of output. So once again, let's put a little table together here. And what we're trying to do is find, again, combinations of labor and capital when put to this production function will give us 100 units of output. So if L is 1 and K is 100, since 1 times 100 is 100, we'd get 100 units of output. 2 and 50 will be another point on this isoquant. 4 and 25, 5 and 20, or for that matter 20 and 5, oops, 10 and 10, and so on. So hopefully you're getting the point here that an isoquant is just showing all combinations of inputs that can produce a given level of output. This is just going to be one of many isoquants. We could repeat this exercise for when output is 50 or 70 or 200 or 1,000 for that matter. So there's going to be a whole map of these isoquants, if you will. So let's take a look at graphing an isoquant. We're going to graph an isoquant in this XY plane here, where on the y-axis we have units of capital, so K is units of capital, L is units of labor. So an isoquant may be for 100. I'm not going to plot each one of these points, but it's going to look something like this in this example. Okay. I'll just put 100 in parentheses here. So this shows us all combinations of inputs that will produce 100 units of output. So I'll just get 1 point over here, let's say. Here, 100 units of capital, 1 unit of labor, when plugged into the production function, which is K times L, gives us 100. $50 units of capital, 2 units of labor, put into the production function, gives us 100 units of output. And like I said, we could do this for 200 units of output or any other level of output we desire. So here's an isoquant showing us all combinations of inputs that can produce 200 units of output. And we could do this for 300 and so on. So one thing you might notice here is that as we get on a higher isoquant, output increases. This is going to be one of the standard properties of isoquants, is that on higher isoquants the firm can produce more output. Okay, let me go to a clean sheet. Okay, the next concept I want to talk that's related to the isoquant is this idea of the marginal rate of technical substitution. MRTS for short. The marginal rate of technical substitution is going to be defined as the amount of capital that can be substituted for 1 unit of labor, holding output fixed. It's going to be, again, the amount of capital that can be substituted for 1 unit of labor, holding output fixed. The best way to think about the marginal rate of technical substitution is by looking at it with an isoquant. So here's an isoquant, and let me put up some values up here. Say 4 units of capital and 1 unit of labor, 2 units of capital, 2 units of labor. So we can calculate the marginal rate of technical substitution between these 2 points. Again, I defined it as the amount of capital that can be reduced or replaced by adding 1 more unit of labor. So in this example, the change in capital here is -2. As we move down and along this isoquant, capital is falling by 2 units, going from 4 to 2, while we gain 1 unit of labor, so the change in L is 1. The marginal rate of technical substitution, then, I'm going to define it in an absolute value. The marginal rate of technical substitution, do it like this. I'm going to define it as the absolute value of the change in capital over the change in labor. Which just equals 2. What does this 2 mean? It simply means, as I stated with the definition, it's the amount of capital that can be replaced by 1 unit of labor. So over this range of the isoquant, 2 units of capital can be replaced by 1 unit of labor, holding output fixed. I will note that your book keeps the marginal rate of technical substitution. They keep the minus sign. Okay. I like to think of it in absolute value, the way we define it. Anyways, one other thing is that this here just happens to be the absolute value of the slope of the isoquant. Okay, so this change in K over change in L, that's just how we define the slope in an XY plane. So it's technically the absolute value of the slope of the isoquant. That's what the marginal rate of technical substitution is. One important property of these well-behaved isoquants is that this marginal rate of technical substitution tends to diminish as we move down and along an isoquant. So this idea of the diminishing marginal rate of technical substitution. Let me do another diagram to illustrate that point. Not drawn too closely to scale here, but that's okay. So we got 3 points here, A, B, and C, and we'll calculate the marginal rate of technical substitution between a couple of these points. So between A and B, the marginal rate of technical substitution, like before, is just 2. 2 units of capital can be replaced by adding 1 more unit of labor, holding output fixed. When we move from B to C, the marginal rate of technical substitution has diminished. It has become smaller. Here, 1 unit of capital can be replaced by 2 units of labor. So it's just going to be 1/2. Okay, capital falls by 1 unit from 2 to 1, but we need now 2 additional units of labor to hold output fixed. Okay, let me label my axes here. So this is going to be a standard property of isoquants, is that the marginal rate of technical substitution is diminishing. All right, before I go on to something else, there are a few other things I want to mention about the marginal rate of technical substitution. It can be shown that the marginal rate of technical substitution is going to be the ratio of the marginal products, the marginal product of labor to the marginal product of capital. Okay, so this is going to be an important point for us later on when we're looking at the optimal input combination. So the marginal rate of technical substitution can be thought of as the marginal product of labor divided by the marginal product of capital. Let's do a numerical example. The marginal product of labor is 60. That is, if we were to hire another worker, output would rise by 60 units. And let's assume that the marginal product of capital is 30. Okay. If we were to hire another unit of capital, output would increase by 30 units. Or if we were to reduce our capital stock by 1 unit, output would fall by 30 units. Just plugging these values into the marginal rate of technical substitution formula, we get 60 divided by 30, or 2. So in this example, the marginal rate of technical substitution is 2. We saw that in this prior example, and it simply meant that at this point on the isoquant that this firm can reduce capital by 2 units and add 1 unit of labor, and its output will remain constant. So 2 units of capital can be replaced by 1 unit of labor, holding output constant. Why does that make sense? Well, since labor is twice as productive as capital, it should make sense that 1 unit of labor can replace 2 units of capital. Again, let me repeat that. Since labor is twice as productive as capital currently, it should make sense that 1 unit of labor can replace 2 units of capital. So indeed, the marginal rate of technical substitution should be given by this formula, the marginal product of labor divided by the marginal product of capital. Okay, I will stop here on this segment of the lecture.